The exponential function is either of is increasing or decreasing. If you have already evaluated f(0), try evaluating f(1). If f(1) is greater than okay. If f(1) is greater than slope is positive and 1 greater than positive. F(x) is I can do that the slope is 3 greater than 2. F(0) oh, 3 gives asymptotes of the if f(x) increases is very large, the rate of infinity. Putting it all together, let's get graph. If you are evaluating by hand, you will put a drink of milk at the pot. Positively infinity finally something left on the graph in sketch. And the point on sketch 1 to sketch a curve establishing the y-axis relevant and the slope. Extend the curve on the both sides, one either across or horizontal slope towards infinity on y-axis. And as it is to do that multiple power x. And where the point of the this maybe like that minus 3 minus 1 and again 0.5. Now this is 0 minus 1 plus 1 0 4 3 check. Measure the points. What's in the graphic and if the cost of 0 and 0 minus 1 0 0 on then 0 0. As x increases, y increases. As the value of x decreases, the y pushes but never reaches to but never reaches to asymptote निरंतर अवस्था है x is as decreases y minus 1 1 by 32 0.0 minus 1. My god, just minus 1, I guess. How do we identify the features of the following exponential graph?
All right, we are asked to choose the graph of the function, and the function is f of x is equal to 2 times 3 to the x, and we have three choices here. So pause this video and see if you can determine which of these three graphs actually is the graph of f of x. All right, now let's work through this together. So whenever I have a function like this, which is an exponential function, because I'm taking some number and I'm multiplying it by some other number to some power. So that tells me that I'm dealing with an exponential. So I like to think about two things. What happens when x equals 0? What is the value of our function? Well, when you just look at this function, this would be 2 times 3 to the 0, which is equal to 3 to the 0 is 1. It's equal to 2. So one way to think about it, in the graph of y is equal to f of x, when x is equal to 0, y is equal to 2. Or another way to think about it is this value in an exponential function, sometimes called the initial value. If we're thinking of the x-axis instead of the x-axis, we're thinking about the time axis or the t-axis. That's why it's sometimes called the initial value. But the y-intercept is going to be described by that when you have a function of this form. And you saw it right over there, f of 0, 3 to the 0 is 1, you're just left with the 2. So which of these have a y-intercept of 2? Well, here the y-intercept looks like 1, here the y-intercept looks like 3, here the y-intercept is 2. So just through elimination, through that alone, we can feel pretty good that this third graph is probably the choice. But let's keep on analyzing it to feel even better about it, and so that we have the skills for really any exponential function that we might run into. Well, the other thing to realize, this number 3 is often referred to as a common ratio. And that's because every time you increase x by 1, you're going to be taking 3 to a 1 higher power, or you're essentially going to be multiplying by 3 again. So for example, f of 1 is going to be equal to 2 times 3 to the 1, 2 times 3 to the 1, or 2 times 3, which is equal to 6. So from f of 0 to f of 1, you essentially have to multiply by 3. And you keep multiplying by 3. F of 2, you're going to multiply by 3 again. It's going to be 2 times 3 squared, which is equal to 18. And so once again, when I increased my x by 1, I'm multiplying the value of my function by 3. So let's just see which of these do this. This one we said has the wrong y-intercept. But as we go from x equals 0 to x equals 1, we are going from 1 to 3. And then we are going from 3 till, looks like we're pretty close to 9. So it does look like this does have a common ratio of 3, just has a different y-intercept than the function we care about. This looks like the graph f of x is equal to just 1 times 3 to the x. Here, we're starting at 3, and then when x equals 1, it looks like we are doubling every time x increases by 1. So this looks like the graph of y is equal to, I have my, we could call our initial value, our y-intercept, 3, and if we're doubling every time, we increase by 1, 3 times 2 to the x. That's this graph here. As I said, this first graph looks like y is equal to 1 times 3 to the x. We are tripling every time, 1 times 3 to the x, or we could just say y is equal to 3 to the x. Now this one here better work, because we already picked it as our solution. So let's see if that's actually the case. So as we increase by 1, we should multiply by 3. So 2 times 3 is indeed 6. And then when you increase by another one, we should go to 18. And that's kind of off the charts here, but it does seem reasonable to see that we are multiplying by 3 every time. And you could also go the other way. If you're going down by 1, you should be dividing by 3. So 2 divided by 3, this does look pretty close to 2/3. So we should feel very good about our third choice. All right, we are asked y is equal to 2. Or another way to think about it is this value in an exponential function, sometimes called the initial value. If we were thinking of the x-axis instead of the x-axis, we're thinking about the time axis or the t-axis. That's why it's sometimes called the initial value. But the y-intercept is going to be described by that when you have a function of this form. And you saw it right over there, f of 0, 3 to the 0 is 1, you're just left with the 2. So which of these have a y-intercept of 2? Well, here the y-intercept looks like 1, here the y-intercept looks like 3, here the y-intercept is 2. So just through elimination, through that alone, we can feel pretty good that this third graph, x by 1, you're going to be taking 3 to a 1. This number 3 is often referred to as a common ratio. And that's because every time you increase
b greater than 1 while 1 line. Like we're supposed to. 0 power 1, 1, 0. As we increase the value of f1 equals to infinity. As we x decreases the value to y equals to 0. X decreases the y value equals to 0. When the graph starts looking so as x increases y approaches infinity fast fast or faster as x decreases decreases to the y value approaches 0 0 0. As when there was a these this one is now 4 times 4 into 0 approaches teacher. Teacher 0 dot 3 x approaches to faster 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 if p is smaller than negative graph is negative slope of one by 2 is then you want to go smaller than 1 there is 0 and then minus 1 0 0 that matter there one is followed for in this case x increases y value minus 0.1 as x increases y approaches 0. As x decreases y approaches infinity. Here's a f of x equal to by 3 and so on. Okay. How do we see horizontal asymptote? Shifting horizontal asymptote. How do we say? The y value approaches both your negative infinity on end and a constant on the other. Y value of the exponential graph. and under infinity on one end and the constant on the other. We can change the constant value y, which is going to be the same constant. Equals to px. So y value of y approaches infinity on the one end, and the value of y approaches infinity on one end and constant and the constant zero on the other. That's why I put it the other one end. The value and constant zero on the other. The zero and zero. तर मैले जिरोलाई रोक्न सक्छु, जिरो नहुँदैन फाइभ बनाउन सक्छु, त्यही त त्यसमा चाहिँ टू हुन्छ होइन, त्यही छ त जिरो भयो भने माइनस भयो भने पनि के हुँदैन, for f of x equals to bx, one end approaches infinity and other end approaches zero. If I want to change the asymptote, I can use d on the other. I can introduce a constant term in the function f of x equals to b of x plus 5. So in this case, one end approaches infinity and other to 5. This is a how do I say y-intercept? Y-intercept पनि चेन्ज गर्न मिल्यो, तर त्यसको लागि चाहिँ यो चेन्ज गर्नुपर्छ। यसमा अगाडिपट्टिको चाहिँ भ्यालु चेन्ज गर्यो भने हुन्छ, जस्तो कि यसमा चाहिँ अलि होला पनि छैन, equals to 0.5 0.5 1.01 ke power fx lah ini dan dari q pasti 1.1 decimal. It passes through the also. For x equals to 0, it passes through 1. तर मैले यसलाई चेन्ज गराइदिएँ र मैले लगाएको थिएँ 5 राख्थेँ अनि 51 होइन ल के हो यो 51 पनि 1x मा 1.2 राख्नुहुन्छ भनेपछि 5 बाट पास हुन्छ यो if I want to change x intercept y intercept I will introduce a coefficient in bx b to the power x and it changes its y intercept. So I have x equals to a times b to the power x will have intercept of a. Uh, this one A is also called the initial value for f of x is
we're told that the graph of exponential f is shown right over here. Declining here, and we can see here we're taking 5/7 to the x. So every time you multiply by another 5, larger and larger. So choice A would actually look something like this. So we know it's not choice A, and choice C looks right because we see this curve right over here is approaching 0, and this would also approach 0 as x gets larger and larger. So we can feel pretty good about choice C here.
아버지는 기원전에 MX가 minus plus 1 plus 1 minus 1 plus 1 x squared 0 is minus 1 so it's x 1 by 3 and 0 is 0 and 1 but 0 is 0 minus 1 and 0 plus 1 and 0 is 0 plus 1 minus 1 1 plus 1 and 0 0 and when I wanted to see when the percent when the export 0 minus 1 minus 4 minus 4
So the function f is actually getting more and more negative. And then as x gets larger, there's two ways that you could approach it. You could think about the behavior of this expression as x becomes very large or x becomes very small. Another possibility is we try a table with some easy values. So let me start actually with the table method right over here. So let me just try some easy x's to calculate and figure out what the corresponding y is when y is equal to negative f of x. So one easy one would be, well, we could try 0, but we could see every one of these graphs have the point 0, 0. Is we try a table with some easy values. It'll then be plus 1, or we could even write it like this. This is the same thing as 1 minus 1/3 to the x. Now, there's two ways that you could approach it. You could think about the behavior of this expression as x becomes very large or x becomes very small. Another possibility is we try a table with some easy values. So let me start actually with the negative f of x. X is very large or x becomes very 1/3 to the x. Now, there's two ways that you could approach it. You could think about the behavior of this expression as x becomes very large or x becomes very small. Another possibility is we try a table with some easy values. So let me start actually with the table to help us differentiate between the graphs. When negative 2/3, that looks about right. So this one is looking pretty good. B, 1 comma 2/3. This is definitely larger than 2/3, so I would rule that one out. 1 comma 2/3. This looks like negative 2/3, so I'd rule C out. 1 comma 2/3. Definitely nothing right over here, so I'd rule D out. So A is already looking pretty good. But let's just confirm -1, -2. -1 looks like the point. -2 is there as well. So I'm feeling very good about A. And you could even check -1, -2. The graph doesn't go through there. -1. When x is very negative value. So when x is very negative, your graph should get very negative. And this one checks that box. As x gets more and more negative, this graph is just really getting more and more negative. And then as x gets larger and larger and larger, more and more positive, well, 1/3 to larger and larger positive exponents is just going to get closer and closer and closer to 0. So you're going to approach 1 as x gets larger and larger. And it looks like that is what is happening with this graph right over here. As x gets larger and larger and larger, y is approaching 1. So once again, we like choice A.
So value y is a constant. And x equals y1 and x equals 2 multiplied with 2 and x the graph of y is 2. Slope what is the integral of screen numbers.